Welcome back everyone. I hope you all had a refreshing break. Now we move on to our next session of the day, which is remote sensing research application and advantages.
This session will be delivered by Dr. A.P. Krishna sir. Let's put our hands together to warmly welcome him on the stage and look forward to gaining valuable insights from this session. Stage is over to you, sir. Let's put a huge round of applause to welcome sir.
Yeah, thank you. Thank you, friends and others present here. So now moving on to the next lecture, which is slightly different in terms of, again I am repeating a review which actually gives some idea about its application part in the sense that we come across many studies in remote sensing usage, that sometimes it may be for a kind of new person, it would just like be a fascinating area where a lot of these things they come across in terms of content, but the point is where are those areas which actually we should focus on. Actually a remote sensing person, what he or she looks for doing maybe as a researcher, or maybe what are the kind of pertinent problems and issues which can be addressed using the remote sensing technologies. So now looking into that aspect, so again my lecture is kind of designed in terms of giving you an insight that in what way, again I am saying remote sensing is important as a research tool, right. So that's the way. I'll not go for very detailed kind of research results and research kind of flow, but some of the kind of findings, maybe a few samples at the end I will discuss. But let us look at this remote sensing research potential. When we say, we hear kind of lot of things happening using remote sensing tools, but what are those areas? Maybe climate change, many times we hear. So climatic changes nowadays, one of the very kind of this pertinent problems we are facing. Desertification processes, means what? Desertification process, once upon a time it would appear like a subject to handle, but nowadays it is a problem to handle, like it is happening. So now desertification is happening, climate change is not a fancy thing nowadays we are experiencing. So where we can contribute more? Forest fires increasing in instances because of all this, glacier melting. So all of these are kind of some of such kind of global issues which are there, and what this tool like remote sensing be doing in this. So those are the kind of questions, and also land cover and vegetation status, they can be observed by virtue of remote sensors. So basically these are all the kind of areas where lot of focus is coming. And when we look at remote sensors, we look at the radiometers, spectroradiometers on each of the kind of satellites, and basically what kind of potential it is being harnessed. It is like a kind of synoptic coverage, large area coverage and different wavelengths. So that is what we already heard in the morning, and multi-temporal capabilities. So these capabilities make remote sensing one of the most significant technology for analysis of landscape and environment towards understanding natural resources and phenomena, prevention, management and mitigation of natural risk such as flooding and landslides, forest fires, volcanic eruption or earthquakes. So maybe it is a kind of indicative list, some of the things, right. So now looking into these particular domains, optical remote sensing at its potential. So that way we will go. So optical remote sensing, when we say, again as we talked in the morning also, so it is basically including the visible and NIR part, and sometimes up to thermal infrared part. So collecting radiation reflected and emitted from observed surfaces. And in this particular range, just focusing on this particular range, data acquisition, that is measurements, signals and images, that basically is realized with sensors which are utilized for the radiation collection through optical instruments. Why it is called optical remote sensing? Because optical instruments are utilized. And then such as lens for reflection or mirrors for reflection mechanisms. So here the kind of setup which the sensor has is optical. And strong interaction of EMR at these frequencies with the atmosphere and the presence of clouds, that constitute an important limiting factor. Now there is limitation of this optical remote sensing on the potential observation of the Earth's surface. Then optical remote sensing, what actually it has got most of the use, it is one of the most important is the thematic mapping, themes of the terrestrial objects, terrestrial kind of observations that we do. So thematic mapping, when we say, that is generally understood as extraction of the value added information from raw or pre-processed data. That is one of the most common and relevant application fields in remote sensing. And then it can be divided into subcategories such as pattern recognition, feature extraction, and thematic classification. So that way one can see that how to proceed with this usage of this. And thematic and land cover maps, which are derived from the remotely sensed image, can support land and environment monitoring as well as management and planning activities. So a lot of this is happening. Actually, this is for the youngsters to appreciate more that these are the areas where things are changing and where actually more and more of remote sensing applications are taking place. And earlier it would have been of academic interest, that some researcher is doing, somebody is doing somewhere, it is there available, so somebody is doing. Nowadays it is lot of it is actually getting into practical domain. And then proper response actions to environmental and climate emergencies, floods and landslides, earthquakes and fires, food and water security. They are based on updated spatial temporal thematic knowledge, especially if accessible in a digital cartographic format. So all of information which are all of these information which are being generated and made available to the kind of common in the common domain which is available. So it is enhancing the potential to a great extent. And such knowledge is useful to the deployment of preliminary actions which may be immediately required, the quantification of damage extension, and the planning of recovery and prevention measures. So that is one part where we talk about disaster management, lot of it in these days. So that is what actually faster response, faster action. So for that, lot of exercises are to be done, which actually are being facilitated using the remote sensing technologies. And availability of thematic maps is relevant not only in disaster management, but it also has a crucial information source for land and environmental management. For example, in forestry, mapping is important for both global monitoring of the fires as well as implications on climate and environment. So a lot of this interconnectivity. And in some policy sectors such as agriculture, thematic maps, they are derived from satellite imagery. They can be used to rule the distribution of support funding. So maybe even the financial allocations to different regions depending on the what kind of assessment which is possible through remote sensing, and that can facilitate the policy level kind of decisions and plannings. Then again, in this optical remote sensing, when we look at this, some of the areas which actually look in terms of what would have been the scenario without it and how it is changing. So maybe relevance of thematic mapping when we look at, so application fields that basically include urban and planning, identification and monitoring of dangerous materials, and then many things. So it is one of the indicative lists, so water availability and many kind of ecosystems that has to be monitored. And again, as I said in the earlier session also, that it in the civilian domain, when we see, it all started in 70s with the availability of remote sensing data from NASA's Landsat satellite. So that actually was the starting point. And then now it is moving on to the next generation satellite constellations specifically, which can provide continuous data for a global monitoring of a daily or weekly cycle. So that is how it is changing. That is the Sentinel satellite series, which is managed by the European Space Agency ESA under the umbrella of Copernicus. And there is one program on global monitoring and Earth observation program. So that is NASA's, okay, the different kind of Landsats. And remotely sensed data and imagery, that actually has changed a lot. So that has grown a lot and will continue to grow and diversify in the future. So that is what is the scenario. From the spectral and spatial resolution point of view, that is one. And then requiring the development of novel analysis and information extraction methodology for the provision of more refined and accurate value-added information. So that is what I was trying to say in the morning session also. Conventional image processing technique for data mining and data kind of extraction. And in addition, now there is more and more emphasis on further machine learning, deep learning, those kind of things. Because of what? Because of dearth of data which is there. So examples of methodologies can be fuzzy algorithm for mapping, automated classification of remotely sensed images, change detection techniques. So these are all to be facilitated through conventional as well as maybe the now state of the art kind of techniques which are developing. Now coming to microwave remote sensing at its potential, that was optical part. The microwave, now it has the unique capability, what actually it has. So one can see that it can give complementary information in some applications and supplementary information on in others to the optical and infrared sensing. So, optical and infrared whatever we are getting, microwave can strengthen that as supplementary. Combination of microwaves, when we look at visible and infrared radiation, that allows a study of the geometric, bulk, dielectric and non molecular kind of resonance properties of a surface. So, these are all actually being picked up, and for some remote sensing applications, microwave remote sensing is unique and has standalone applications. So, now it is only microwave. So, that is also happening. Earlier it was considered a supplementary. So, microwaves has capability to penetrate clouds, that is one very important characteristics, and microwave sensors can penetrate clouds, and so they can operate in all weather conditions. And frequencies above 15 gigahertz have effect of water clouds, and frequencies above 10 gigahertz are attenuated by heavy rain. So, in fact, those are the kind of divisions in between, and microwaves are basically independent of sun as source, and so microwave sensors can detect objects in day as well as in night. And then microwave sensors receive signature which are generated due to self emission in case of the target, which is self emitting. So, some of the objects they emit. So, and then in case of scattering coefficient, the physical properties of target give different coefficient for different angles of incidence and polarization, how it is falling and it is interacting with the object. Thus, it does not require sun's illumination, and so the target properties can be studied during day as well as in night. And microwaves are capable of penetrating more deeply into vegetation as compared to optical waves. So, it has that capability also. And in case of microwaves, the longer wavelengths penetrate deeper through vegetation as well as soil, longer wavelengths. And depth of penetration is more for very dry vegetation and dry soil. And then penetration reduces the smaller wavelengths. And penetration decreases with the increase in the moisture content in vegetation and soil. So, those are actually becoming the basics of identification and understanding the characteristics. And then microwaves are sensitive to the moisture content. So, these are the plus points, and depth of penetration is function of moisture content in the soil. And microwaves are sensitive to the presence of moisture in the soil as well as in vegetation or any material which absorbs moisture. So, anywhere. So, that is one of the very prime kind of these properties, and this actually happens due to the variation of dielectric constant of the dry material and that of water. So, because of this dielectric properties, so it is varying, and then dielectric constant of dry soil varies between 2 to 3 depending upon the texture, whereas the dielectric constant of pure water is around 80 at room temperature and at around 1 gigahertz. So, therefore, dielectric constant will vary between dielectric constants of dry soil and of the saturated soil, which is around 30. So, therefore, one can measure the moisture content in soil by measuring the dielectric constant of the soil. So, these are very good properties in that sense. And then application wise, terrestrial applications, when we look at it, is one application is soil moisture estimation, then crop identification, flood mapping, snow studies, geology, forestry, urban land use, hydrocarbons. In oceanographic applications, sea state measurement, how it is, and then measurements of sea surface salinity, topography in shallow sea, wind speed over sea surface, ocean circulation, wave height, oil pollution, and then sea surface temperatures, geophysical parameter retrievals, ocean geoid studies. So, these are some of the areas where a lot of microwave application is there. And then atmospheric applications, when we come, this area is accorded a high priority in terms of microwave remote sensing. Other applications of interest include profiling the moisture and temperature in the atmosphere, which is essential for delineating mesoscale climatic systems. So, this is also another atmospheric remote sensing kind of application. And application for studying the minor constituents in the atmosphere is important for stratospheric research. So, that is within the atmosphere. And there are kind of applications in the Indian monsoon studies, monsoon temperature profile, atmospheric minor constituents. So, these are in this domain. And talking about some recent trends of remote sensing research, significant application areas, one can see the enumeration of the areas, that agriculture, water resources, urban planning, rural development, mineral prospecting, environment, forestry, ocean resources and disaster management. And significant research areas out of this: climate variation dynamics, remote sensed image classification. That classification itself is also a research. And then prediction and evaluation of natural disasters, monitoring of Earth state using deep learning techniques, then 3D or 4D data collection, analysis and classification, mapping and semantic segmentation using remote sensing images, urban area classification based on climate conditions, then geographical this basically the data intensive geographical this urban applications, that basically is in terms of urban design and plan, then the kind of vehicle mobility in urban area transport, and monitoring environmental status of the urban area. And then now looking at some of the kind of specific ones which are more, we come across more of it, these applications, environment and conservation. Here talk about the deforestation patterns. Basically it takes into account the tracking of the practices of deforestation and their effect on climate and biodiversity using remote sensing. And then basically it is using the spatial patterns of deforestation which can be visualized and examined periodically with the support of GIS. So based on that platform. And wetland ecosystem assessments, where transformations in wetlands. Wetlands are very important for us in terms of our this ecology and environment. So that is now that is being impaired. So that wetland study evaluation with the help of remote sensing. So representing and examining the impacts and regions of wetland degradation using GIS. Then glacier volume and ice melt analysis. Glacier volume actually is nowadays becoming more and more important, because you might have heard that it is because of the global warming and climate change kind of scenarios, one of the very vital components which actually giving the idea about the global warming. So if glacier health that we say, if it can be tackled dynamically, that will give a very fast kind of information about climate change impacts. So that is one. Assessing effects on freshwater resources and global sea levels, that is one. Changes in ice melt rates and glacier densities using remote sensing data. So a lot of it, how the resources will change, how the kind of impacts will be there. And then urban planning and development, smart city planning. In this, towards enhancing resource handling and framework for smart city planning, combining different data sets such as public services, then traffic flow and density of population along with remote sensing and GIS. Then urban heat island effect impacts, that basically utilizing thermal remote sensing data. The impact of urban heat island is an important area to examine. That is, and then urbanization and land use change analysis, interpreting development patterns and awareness about upcoming progression strategies, analysis of previous land use transformations in city regions using GIS and remote sensing. So a lot of it. And natural hazard and disaster management, another important focus area, in which flood risk and vulnerability mapping, where the maps to be developed in terms of flood risk maps, integrating remote sensing along with GIS. So that is particularly for the awareness of emergency readiness and response policy by detecting the risky frameworks and populations. So nowadays a lot of emphasis on disaster management as a proactive kind of activity, where already the kind of disaster management activities require disaster management plans to be prepared, and this risk map is very important, and that is where that remote sensing and GIS, they have a very great role to play in terms of identification of risk zones. So, and then forest fire detection and spread prediction. Similarly here also identifying wildfires using remote sensing and utilizing GIS based models to forecast their distribution and facilitate the fire management and elimination planning. So, lot of planning for that. Earthquake damage assessment. Earthquake damage basically is to be done evaluation in a faster and rapid manner. So, that is being facilitated using this remote sensing data. So, here basically implementation of remote sensing data, which actually we say is mapping the impacted regions after the earthquake has occurred and focusing on rehabilitation and rescue. So, that actually is an important component of disaster management. Then natural hazard zonation and risk assessment in general. So, any type of hazard. So, using high resolution remote sensing data, hazard zonation as well as risk zonation, that actually using the GIS for better disaster management. So, basically the areas where the kind of earthquake proneness is there, landslides proneness is there, flood and forest fires. So, for such areas, and that is not the only list, it can be grow, but some of the vital ones. And farming and forestry, precision agriculture and crop health monitoring, here using remote sensing data and GIS technology for tracking soil moisture and crop wellness, supporting smart farming to enhance the usage of resources. So again here, forest biomass and carbon stock estimation, assessing carbon levels and forest biomass using remote sensing and GIS analysis. This basically allows the preservation and reduction strategies for climate change. So now this is linked to the climate change scenario. So in which these studies can help a lot. Pest infestation mapping in agriculture, identifying pest outbreaks in crops using remote sensing and GIS for pest management interventions and examining spatial trends, how it is happening. So that entire details to be worked upon. Then water resources management, one of the very vital ones, water quality monitoring in lakes and rivers, that is various water quality based parameters such as chlorophyll levels and turbidity to be evaluated using RS and spatial analysis. Snowpack monitoring and water supply forecasting, monitoring levels of snowpack, again as we talked earlier, so that is in a different domain, but here also dedicated to water resources using remote sensing and GIS. So basically leading to water supply availability in downstream areas to be designed and forecasted, because lot many rivers, say for example snow and glacier fed rivers which are coming from the maybe Himalayan area in India. So if everything is okay in the upper catchment, then probably the perpetual supply of water which is being there for the downstream areas has to be sustained. If something is going wrong there, then that actually is going to be impaired. So what supply for agriculture, for drinking water purposes, anything which is coming downstream and to be available to various cities situated along the river and the various areas depending on the agriculture for the irrigation from that. So that will be in the long run impaired very badly. So that is why that catchment area helps. So there also it's snowpack monitoring and water supply forecasting. So these are all, lot many modelings are there in which remote sensing input goes for hydrological modeling, and then that actually works upon including the inputs from you say precipitation, not only rainfall, snow precipitation also, and condition of the catchment area in such areas. Then groundwater potential zoning with the aim of enabling sustainable water resource management, detecting possible areas for the retrieval of groundwater by integrating remote sensing with GIS. So here also a lot of modeling exercises involved, in which lot of parameters to consider, lot of good models are there, and that has to be used to work upon this groundwater potential zoning. Then you have climate change and ecological effect. Here again simply talking about sea level rise and impact analysis. So monitoring increase in sea level, so that basically remote sensing can allow, and that impacts on environment and coastal population. So gradually I think we are hearing a lot of this these days because of the global warming, melting of ice, and then the rising of the sea level, and the kind of coastal areas and those areas are going to be impacted. So that monitoring for that and impact analysis for that. Monitoring of solar and wind energy potential also. So possibility of wind and solar power to examine using remote sensing and GIS. So basically this enables adaptation of renewable energy sources. Carbon footprint mapping of urban areas to map carbon discharges from various urban infrastructures, green cover, and its effect on city carbon footprints to be evaluated with the help of this. So these are all some of the important areas where this research is actually going on. So I am talking about very broad, but there could be many within that. So one has to look at. So these are the areas areas of greater concern here. And now coming to this part, actually I was talking about Google Earth Engine, because see basically what is happening is okay. Now remote sensing data, how all of a sudden it has become so important. There used to be some people doing something in remote sensing, they were concerned, okay, some imagery has to be there, we have to study that, find out something. Now actually this is another phenomena in which in the public domain lot of freely downloadable, freely available remote sensing data is there, and which is huge. We are talking about petabyte, and those kind of size of data, that much quantity of data is available, and lot of good data which are not actually being used so much as the quantity and the information which is available. So nowadays it is almost coming into a domain where everybody concerned can use the data. So now Google Earth Engine, that is why it has come into picture nowadays, where there is a cloud platform which is allowing the accessibility to data, as well as you do all the analysis in the cloud based software also. So you don't need to have your own software also for many things. So that is why it is becoming very important these days. So basically, one of the most important component of it is satellite imagery. That is one of the most useful geospatial data layers available today. So we have a lot of it. Then it is still very difficult to deploy maybe effectively over the various computing platforms available to GIS systems and users, GIS users rather. And then geospatial researchers and professionals, they seek to make use of imagery and other very large raster data sets in an analytical framework. And they need to do more than simply view, zoom, pan and rotate into 3D views. So that is now gradually becoming conventional. But for learning, we have to go through that. So until we learn that, how do we go for advanced level? But there was a time when that was enough. But nowadays, that is not enough. That is only part of learning, but we have to go beyond that. And they seek to run image processing and analysis algorithms to extract information and features to be used in scientific research, modeling and decision support systems. So that is the context how it is related. Now coming to this Google's cloud platform, basically it is a kind of platform which is for easy petabyte scale analysis, petabyte. So in that range you go. So now here data wise, that is an exhaustive catalog of remote sensing data sets including multispectral, radar, aerial, climate, land cover and vector. So not only RS data but other data also which are being pulled in and it is available. And then computation, so co-located data storage and computation, it is done on the same platform. Then come to API, that is application programming interface, which is there, that simple but yet powerful JavaScript and Python API, 2 blocks, JavaScript and Python. So and then browser based integrated development environment, so no software to download or keep up to date, all you need is modest internet connection. This is what is the platform, Google. So this is now almost like a kind of apex geospatial kind of this facility which is there, internet based facility. So remote sensing research, when we say now what can be done in Google Earth Engine. So one can see image processing, map algebra, kernels and convolutions, spectral unmixing, pan sharpening, gap filling, data fusion, so that it can do vector processing, zonal statistics, spatial joins, spatial query, terrain processing, slope, aspect, hillside, hill shadow analysis, time series analysis, extract time series, trend analysis, time series smoothing, temporal segmentation, then object based image analysis. So gray level occurrence matrix, that is GLCM, texture, hotspots. I think gray level by now everybody understands, so that's what I was trying to say in the morning. And then change direction, spectral distance, change classification, class transition. Then machine learning, supervised and unsupervised classification, linear regression, PCA, principal component analysis, and deep learning, DNN, object detection, etc. What it cannot do. So it can do some things, it cannot do some things. So here it cannot create cartographic outputs, right? So instead use the Google Earth Engine plugins in QGIS to create maps. Now you have to use the so you have to somewhere depend on that also for your maps. Then 3D visualization and analysis it cannot do. Then it cannot run hydrological models, for example rainfall runoff modeling and analysis, watershed delineation, fill depression, etc. So that basic things you have to get from somewhere. Then photogrammetry, that is orthorectification, point clouds, it cannot do. LIDAR processing, LIDAR, that light detection and ranging, so LIDAR it cannot do. SAR, synthetic aperture radar interferometry, SAR interferometry it will not do. So Earth Engine does not support images with complex values, so that is what is the limitation also. So coming to this, basically what is Google Earth Engine is an example of cloud based image service which combines an extensive archive of satellite imagery, historical and current, with application programming interfaces that allow analysis to be performed on this imagery without having to move it to the user's desktop. So in the cloud you are doing. Then GE applications include both large scale and relatively small scale interpretations of images and time series of human activity and influence, for example agricultural environment, human built environment, effects on air quality and surface temperature in cities, health and humanitarian activities, It is also useful for hydrological patterns across large areas with reduction of subsurface resources like groundwater, cover of the sea floor, rapid changes to detect through time series such as floods as well as hydrological systems assessment. In terrestrial domain, active fire monitoring using multi-sensor data, forest degradation and deforestation, researches on long time series basis, rangelands, mangroves, natural resources research, etc. So, lot of research. So, it is basically a boon for the researchers, GE. So, it is not that I am advocating only GE here, it is we are talking about remote sensing at GIS only, but GE is something like when you move to the advanced level, researcher level, then I think this is a boon that way. Now, some quick application and usage. So, I will not take much time here, but I will just tell you about something like what is possible in agriculture. You see the soil moisture. So, we already talked. So, a lot of this microwave remote sensing based kind of example that usage here, and both sensors active and passive, and then there is some usage of maybe some soil moisture and ocean salinity kind of sensors. So, these are all different ways in which one can see that how the agriculture can benefit in terms of this moisture kind of details which can be obtained. And of course, basically satellite imagery, when we talk in the agricultural sector, basically it provides insights about crop health again, and soil moisture, weather patterns, facilitating the precision agriculture. So, for all of this, lot of analysis in this domain is possible. Water resources, of course, water quality as well as overall kind of that large region that it can cover, and overall environmental problems and potential kind of health risks through the analysis of changes in water quality. So, regional level. Then basically again looking at some of the other details in which you have the kind of dam break or dam based studies, coastal microplastics, sand submergence, river embankment, etc. can be done during drone based using this drone based high resolution image, and of course lot of this way in which it has to be factored further into analytics. So, one quick example of maybe Prisma hyperspectral versus Sentinel, so multispectral. So, some kind of data where Prisma was something which was a precursor to Sentinel multispectral, that is hyperspectral earlier, but better than multispectral. So, one example here how it can differentiate between the kind of water this overall kind of variation within the water quality. And urban studies, of course, here also maybe it is one of the another important applications as I already talked. So, here one can see you have to lot of research which are actually being carried out, in which new kind of new remote sensing tools are being used. 3D analysis with LiDAR data is one such area. So, here this also has a kind of availability of the data into GIS somewhere, the interfacing, and integrate building information modeling BIM, that is with CAD and GIS. And then these things are there, real time and big data analytics which are actually happening. So, this basically is it is within the domain of GIS, real time data feeds to ingest from Internet of Things, IoT. So, those things are all new growing areas, and particularly AI and ML work with deep learning, they play a significant role while identifying maybe the urban landscape, traffic, 3D live traffic movement, site suitability analysis, ship harboring and industrial mapping or mining. So, these are all not exhaustive, but many of the quick examples. And then here also you can see maybe the kind of object based image analysis, classification of settlement and other land use features. So, here basically using LiDAR based classification. So, some things which are actually possible to do, even the latest data, and that can be put to some specific type of applications and analytics. Disaster management, of course, as I already talked. So, maybe a lot of different types of data which are going to be useful for this. And of course, nowadays it is moving into the web GIS domain, where actually the GIS which is there. So, some of such examples in which it was deployed practically was during COVID-19. Okay. So, here you can see SAR interferometry polarimetric representation of post earthquake on the left side and snow avalanche on the right side. So, maybe these are the kind of data. Then something new, planetary exploration also. moon remote sensing. So slightly I'll touch upon this also at the end. So lunar remote sensing. In fact, I have been involved in two such projects, one on Mars, one on Moon. 2 PhDs already produced on that. So some of the findings out of that. So here actually, I would not like you to be concerned with Moon or Mars remote sensing, but only just to keep your interest alive in these areas also. But you can see where actually the kind of what lunar remote sensing we say, whatever images were acquired during Chandrayaan 1, Chandrayaan 2, based on that. Chandrayaan 3, probably you know, it had a planned life of what duration? Any idea? Chandrayaan 3. So suddenly shift to planetary remote sensing. 1 lunar day equivalent to. This is very correct. 1 lunar day, 14 Earth days, right? So that is the only planned life. So within that also some data has been acquired, but those data, actually the landing was the main challenge here. So what lander has acquired the data, that is becoming available to us, which we are depending for validation with other countries, kind of these probes which had actually gathered data. Now we also have some data. So that also is another area where work will go. But Chandrayaan 1 and 2, based on that, some kind of surface composition of the composition of the moon surface. One project was done, because the big challenge was that was not like these imageries that we are talking, different way to handle. So what kind of radiometric, what responses it had picked up. So that correction itself was big challenge, how to correct it and how to get the real response of the objects. So that was the project. So then it may look very preliminary for Earth, but for that it was a big thing. So one scholar worked on that, and he already got his PhD awarded on that. And another on Mars, in which Mars has a very peculiar type of environment, dusty environment, and then a lot of wind activities are there. Even you can say the kind of dunes, sand dunes are found there. So sand dune studies and wind activities. So based on some kind of data, and so that was also worked upon. Two research scholars have got PhDs there. I think Dr. Milley you might have heard. So we did it together. So that was, so we did 3 PhD students and those 2 projects. So anyway, but that is another story. But only to keep your interest alive, even the planetary remote sensing is there. So that is very interesting to see. So in which what you can see, some kind of craters to be detected on moon. So some specific studies, so what type of data can be useful. So those things we did, and overall kind of detection, how it can be improved. And so those are the challenges. So now even our Chandrayaan 3 and Chandrayaan 2 also have one sensor, that is DFSAR, dual frequency SAR. So that is something very unique. So very few in the world have other countries. So we also have got the DFSAR, and now that is facilitating some kind of studies. So that is, so one result from that, how it can improve. So I think up to that. Thank you. So application wise, the conventional applications, yeah. And taking you up to the planets also, to some extent I tried, but my idea is you get connected to it and you feel that there is something useful and what you can do as a researcher in the future. Thank you. Thank you. So,
Any question?
and then, yeah. Mike.
Good afternoon, sir. My name is Kapil, sir. I'm a student of Engineering branch of ARSGISR-2024. So my question is that how can we integrate the hyperspectral data with the GIS layer so that we can get the information of land use pattern and other type of challenges like dimensionality and spectral.
Yeah, one part is taking out information from hyperspectral itself is a challenge. Once you do it, because the problem is not doing the thematic mapping, problem is handling the huge amount of data. Say for example, I'll say I want to cover on the ground maybe 5 kilometer by 5 kilometer using a multispectral data. So the quantum of data would be less compared to hyperspectral, but I will not be able to handle that much of hyperspectral data in one go. Then I have, and then they are providing in thin steps. So you have to mosaic lot of hyperspectral data, or you do it separately, then you reproduce the entire scenario. So it is still challenging. Hyperspectral, I am saying, even though it has got a lot of interest, and that is what is the research challenge there. So, but the thing is, like, the moment you are ready with your thematic details, that can come onto any platform. GIS, of course, is a kind of common platform where you gather the details as layers, okay, thematic layers. So once hyperspectral data interpretation is complete and you are ready with your classified data, that can become one thematic layer. So that can go there, then you can add another layer with some different information of the same area, and then multiple layers you can handle in the GIS.
So that can be done with the software you just mentioned?
Yes, it's possible.
Okay, thank you.
And Google Earth Engine also one can explore. Google Earth Engine, there the hyperspectral part and those things, the best possible potential what you can use out of that. Actually, the desktop thing, when you do, that challenge is there because it's a huge amount of data. Even the kind of workstation, if you use hyperspectral data, sometimes may be troublesome to use, but at least workstation. Desktop will be difficult.
Yes.
Yeah.
Thank you, sir.
Any other queries? Okay. No more queries. Thank you.
Thank you so much, sir, for your insightful session. Your detailed explanation and real-world examples truly made this topic come alive to us.
Next, I invite Dr. Iqbal Sheikh Sir, Assistant Professor, Civil Engineering Department, PIT Sindri, to present the vote of thanks. Please welcome sir with a huge round of applause.
Good afternoon, everyone. It is my privilege to stand before you to propose the vote of thanks for our esteemed speaker, Dr. A.P. Krishna, Professor BIT Mesra, for invaluable session he has delivered during the workshop. Dr. A.P. Krishna sir, your insights on the topics, advanced tools and techniques of remote sensing and technologies, application were not only enlightening but also profoundly imparting to us. The way you broke down the complex ideas into practical, actionable strategies was truly commendable. Your expertise and the passion have left us inspired and equipped with fresh perspectives. We deeply appreciate the time and effort you invested in preparing and delivering the session. Your thought-provoking ideas will undoubtedly resonate with us as we have learned today. On the behalf of everyone present, I extend our sincere gratitude for your generosity in sharing your knowledge and for your willingness to engage with our questions and concerns. We hope to have pleasure of hosting you again in the future. Thank you once again. Let's all join in giving Dr. A.P. Krishna sir for a warm round of applause. Thank you, sir.
Now, I would like to invite Dr. Jeetu Kujru sir, Head of Civil Engineering Department, BIT Sindri, to present a memento to Dr. A.P. Krishna sir. Sir, please.
Please join me in welcoming sir with a huge round of applause. Thank you, sir, and thank you everyone for your active participation in today's session. Next, the participants are requested to move to computer lab of Civil Engineering Department, and all the second year students